Okay, we're on, and we're going to do another mechanism. Okay, now, just to reflect, impressions represent the number of people your video has been shown to. Is that what it is, dear? But not viewed, then. They haven't viewed it. Okay, I should shut up, shouldn't I? Because I'm recording now. Anyway, the first one we did was free radical substitution. Okay, and that's alkanes, and that was we're changing an alkane and we're reacting it with chlorine in ultraviolet light, remember? And what happens is, oh, I didn't mean to do that. What happens is a chlorine goes on, and there you go. There you go. There's my chlorine on the end. And that was free radical substitution. A quick summary of that is there's initiation, there's propagation, and there's termination steps. We get free radicals, which are not charged, are they? I think that's all I can be bothered with that one. That's free radical substitution. The second one we did was electrophilic addition, and that is alkenes. Okay, and what that is adding things across a double bond. And the thing we added across the double bond was bromine. Okay, and then what do we get? We get this, don't we? Bromine across there and bromine across there. So these are the two we've done so far. Now, as you remember, these are known as mechanisms. And what we do with mechanisms, we show electron movement, don't we? We show what's going on. These are how the electrons move. All right, that's electron movement. So we've done free radical substitution. We've done electrophilic addition. So the next one we're going to do is one called nucleophilic substitution. Okay, now this is a lovely one. Okay, now nucleophilic. First of all, let's have a look at reaction. Let me have a look here. Let's use orange for this. All right, I'm going to start off with a halogenoalkane. Okay, I'm going to use the bromo for fun. Oh, no, I'm not. Okay, I'm going to use a bromo down here. No, I'm not. I'm going to put the bromo here, and I want to use a different color for my bromine. Okay, there you go. Now, these guys, as we should know, or maybe I haven't made a big deal of it, but I should have told you, this type of compound is known as a halogenoalkane. Okay, because it's a halogen on an alkane, basically. So they're called halogenoalkanes. Okay, and they're very, very important class of chemistry. All right, and there's a bromine on this one, so everything's cool there. All right, now what's interesting? Why are these interesting? Well, because the alkanes, and this is an interesting point, because of the halides. Halides are very, what's the next word? Anyone? Quickly, 5 seconds. 5, 4, 3, 2, 1. Everyone's too slow. Halogens are very electronegative. Okay, and that means they pull electrons towards themselves. This means they pull electrons towards themselves. How do you spell selves? All right. So, and that means the halogenoalkanes are, therefore, they have some degree of polarity. They are polar. Alkanes are non-polar. Halogenoalkanes are polar. Thumbs up, thumbs down, please, quickly, while I'm rushing around. Good stuff. Well done, Tamani. Lungi, excellent. So what we have with these guys is we have, this is a little bit negative and this is a little bit positive. So we have a polar bond, and that's attacked by things. Now, it's the carbon that's going to be attacked. Okay, and the carbon, in this case, we're going to do a hydroxide ion. There's an OH minus ion. Okay, there it is, and its lone pair there. Now, this one, and I'm going to use a different white today, is going to be my electron movement. These negative electrons on the OH minus side are going to attack that carbon. Okay, now the carbon is positively charged, or it's delta positive, isn't it? So that carbon is partially positive, delta plus, okay? And therefore, we call the thing that attacks it, this OH minus ion, we call this, or we need a different color here, don't I? We call this, the OH minus ion, this OH minus ion is a nucleophile. Okay, now nucleophile means they attack things of the nucleus. Now, the nucleus of an atom is positive. Okay, it's a bit of a strange name to call it, I must admit. But that means they attack positive things. Electrophiles attack negative things. Let me write it over here. Electrophiles, they attack negative attack. I should use the word attack. Negative things. Nucleophiles, these attack positive things. So my OH minus ion is a nucleophile. It's attacking a positive thing. And it's the lone pair. Now, nucleophiles, now, let's have a closer look at nucleophiles. They must have a lone pair. That is essential. They must have a lone pair. And secondly, they don't have to have this. They may be neutral or negatively charged. Okay, but that is essential. They've got to have a lone pair, but they might be neutral or negatively charged. I'll give you an example of a neutral one. Well, water. Water is a neutral one. Ammonia, that's a neutral one. Why are they nucleophiles? Because they both got lone pairs on the oxygen and nitrogen, respectively. Are we all good with that? These nucleophiles, okay? Are we all good? Good. Thanks, Janet. All right, everyone's good. Well done. All right, so these are nucleophiles. All right, I've drawn a lot there, haven't I? I must admit, I've got really nice writing. I think it looks really nice on these boards. I know I'm being a bit vain there, but I do think I've got nice writing. Anyway, so let's do the show. This is the show, and I'm going to rewrite my bromo, propane. There it is. Okay, here we go. And this is the reaction. Let me do the reaction first. And I'm going to react this with sodium hydroxide. Okay, and the sodium hydroxide is aqueous. And what I'm going to get is I'm going to get this. All right, I'm going to get my molecule here, whatever this is going to be. And that, the OH goes on. And if the OH goes on, obviously the Br must come off. And we're going to end up with NaBr. Okay, so we're all good with that. That's the reaction we're looking at. This reaction, by the way, is known as, let me have a funny color, this is known as a hydrolysis reaction. I'll explain that later, but this is a hydrolysis reaction, and we're hydrolyzing a halogen to form, this is a halogenoalkane, and it's going to form an alcohol, isn't it? Okay, now I know we haven't done a big deal on these, but we've got to start brushing up on them. Halogen alkanes are often shown as that's not right at all. These are known as RXs, where X is a halogen. Okay, do you understand what the R means there, guys? Do we remember what the R means in RX? Thanks, Tamani. All right, the rest of you, if you don't understand, you've got to have a thumbs down, guys, That's the only way we're communicating with each other. So Tamani, I love knowing that you understand, but thanks, Shane. You've got to, if you don't understand, thumbs down. If you do, thumbs up. Okay, otherwise I won't. Oh, all right, Lungi. Right, R means an alkyl group. Okay, an R group, that is an R group. Okay, an alkane is an R group with a hydrogen on. An alkyl group is just an alkane without a hydrogen. It's the bit that sticks onto other things. Okay, that's all we mean by an R group. So if RX is the formula for a halogen alkane, anyone want to tell me quickly what the general formula of an alcohol is? 5 seconds, 5, 4, 3, 2, 1, too slow. it's going to be ROH, because there's an R group attached to an OH. Okay. Now, an R group is what we call an alkyl group. Okay. All right. Now, there you go. So that's an R group and that's an R group. All right. So here we go. There's beautiful. All right. So let's do the mechanism now. Okay. Now, I know it's a lot of writing, but, you know, this is, whatever. This is quite involved, this one. So there's the BR. Now I'm going to do the mechanism. I haven't done the mechanism yet. I've said it's a hydrolysis, but I haven't done the mechanism. Okay. Now, where's my thing? This thing here. This is my OH. This is from the sodium hydroxide. And I've already changed the colours, haven't I, for this? This attacks this. There's an arrow there. Why does it attack it? Let me show you why it attacks it. And you've got to do this. This is delta plus, this is delta minus. You've got to write those delta pluses and delta minuses. Now, as it attacks it, these electrons jump onto the bromine. Okay? So we get this. We get this weird thing here. I keep changing colours here. I don't know why. I can't keep to the same colour. There we are. Now, this is often how we show it. This one is the OH. This is the bond being formed. And I need a different colour. Let me go for this green one. This one is the bond being broken. Okay? Now, the whole thing is negative. Whole thing's negatively charged because the thing that came on to add was negatively charged. This guy is negatively charged. So we've got to have a negative charge. The whole thing gets the negative charge. So what do you think happens now? Anyone know? The OH has gone on. What do you reckon happens now? Anyone? Yeah, go on. Yeah, bromine? Yeah, it does. And look at this. The electrons go onto here fully, like this. Actually, let me do that a different way. Apparently, I can have arrows. There you go. Oh, let's have a look. Will this work? This. Oh, there you go. That's good, isn't it? It gives me my own arrows. The bromine leaves. Well done. Well done, Tamani. You're good at this stuff, I can tell. All right. So, what do we get? We get this guy down here. Okay. 1, 2, 3. Yeah, that's exactly what happens. And it's a full curly arrow, isn't it? So it means 2 electrons, if you remember. We get the product. Oh, that's not right at all. We get, Tamani, your microphone's still on, by the way. We get the OH, and the Br minus comes off. And there we go. That's the mechanism. Okay, it's very straightforward, really, isn't it? I'm gonna make it more complicated in a minute. Don't worry about it. But it's beautiful. I think it's beautiful. Okay. Now, what is it known as? Well, first of all, you should all realise it is a substitution reaction. Okay. Now, what does a substitution reaction mean? It means one thing, the OH, has replaced another thing, the Br. Okay, this guy there. One thing has replaced another thing. It has substituted it. Now, the original OH minus attacked the positive charge, so we call it a nucleophilic substitution. Okay, this is a nucleophilic substitution. All right, now, it's hard to get your head around this stuff, but this is what we got to do. Okay, so that's a nucleophilic substitution. Does anyone, what kind of bond is this? I think it was Tamani that mentioned it last time, or Janet. This bond here, what's special about that new bond? Anyone, you can type it if you want. What type of bond is it? No one? Okay, no one? All right, maybe you're typing at my refresh rate is slow. That bond is I'm going to say the word in 3 seconds. It's a dative bond. Okay. Now, why am I making a big deal? Coordinate. Well done, Janet. That's exactly what it is. It's a coordinate bond. Now, why am I making a big deal out of that? Because in nucleophilic substitution, the lone pair, this guy here, that's why we must have it, because this lone pair is going to form our dative bond. And that's why it must have a lone pair. It must. It's no joke. It's got to have a lone pair. So we're all good with that. So are we okay with that for now? It's going to get more complicated, I'm afraid. Okay, but we're good for now, are we? Excellent. Well done, Lungi. Do we use the same initiation? No, we don't. That is specifically for free radical substitution. Okay. All right. That's not for nucleophilic, whatever this is, nucleophilic substitution. Okay. All right. Now, here we go. All right. Now, it's hard, this, but it's lovely. Okay. So I'm going to draw 3 halogen alkanes. There's 1 bromo something or other, whatever I'm going to make this. There's bromo. And while I'm writing these, you can tell me their names if you want. Oh, am I going to do the hydrogens? I've just realized I'm doing the hydrogens. I think I have to do the hydrogens here. All right. Figure out these names as I'm going along. What's the name of that one, the one on the left? What's the name of the one in the middle? And what's the name of 1, 2, 3, 4? What's the name of the one on the right? Names aren't a huge thing in your course, all right? And I was reading your book, the book you've been given, your IB book. Oh, they go nuts on names. There's pages and pages of names. I wouldn't overdo names, eh? It's nice if you know the names, but don't spend the rest of your life learning these names. All right, they don't go nuts on them. The book goes nuts, but the course doesn't really. Anyway, right, no one's written anything down, so I'm assuming you're either gone away or you don't know the names. The one on the left is 1 bromo propane. The one in the middle is 2 bromo propane. And the one on the right is, there's a methyl and a bromo, isn't there, on my propane. So this is also propane. All right, 1 bromo, 2 bromo, 2, 2. Oh, it's not quite that. You get these so close. All right, you've got a bromo. You're quite right, at number 2. You've got a methyl also at number 2. Okay. So they're both at number 2. You're quite right. They are both at number 2. Okay. So what goes first, the bromo or the methyl in my naming? I don't know if I've mentioned this, but here goes. We've got to learn this anyway. What goes first? I've got to mention bromo first or methyl? Yeah, bromo first, purely because B comes before M in the alphabet. So this guy is called 2 bromo, 2 methyl propane. 2 bromo, 2 methyl. Now, we only put the 2's next to each other, 2, 2. We only do that if we have 2 bromos or 2 methyls. So if this was 2 bromos, 2, 2, dibromo, it would have to be dibromo propane or whatever. I don't think that's, you can get that here. Okay, does that make sense? You only put the 2's next to each other if it's referring to the same species. Okay, which is a bit odd, isn't it? So this one's actually called 2 bromo, 2 methyl propane. Guys, you know what? Don't kill yourself with names, eh? They will, you'll just learn those as you go along. Now, can you see, we've done this before in a previous video. What's this bromine attached to? It's attached to a CH2. What's this bromine attached to? It's attached to a CH. And this bromo is attached to a C. Okay, so the one on the left, as you know, is known as a primary halogenoalkane. Alkane. This one is a secondary halogenoalkane, and this last one is a tertiary halogenoalkane. Okay, it's primary, secondary, and tertiary. Now these matter. These designations matter. Primary, secondary, and tertiary. Okay, now I'm going to go up to here. Okay, and I'm going to take a snapshot of this. You'll see what I'm doing in a minute. Okay, because I don't want to redo it if I can help it. I'm going to copy it. Oopsie daisy. And I'm going to push this up. And now I'm going to paste it. And there it is. And now I'm going to move it a bit, even though I don't know whether it's my processor speed or the internet. It's very slow moving this, as you can see. I've got my processor is pretty good though. I've got a solid state drive, and I've got quite a lot of RAM here. Okay, but it's taking a long time, isn't it? Oh, and it seems to have. Oh, there you go. All right, so there you go. So what was this then? This one was a primary, wasn't it? Well, when we did this before, this is a primary halogen alkane. Primary. Okay, and I'm going to redo this. I'm going to rewrite this mechanism in a different way. I'm going to use everything's going to be exactly the same. So if you're thinking he's done this before, I have done it before, but I'm doing something very special here. Okay, so now let's move this up. What are we using? 1, 2, 3. All right, I'm going to show some stereochemistry here. All right, so now I've got my bromine here, and it is attached to my carbon. And you remember this was a CH2, so this is an H, and that's an H, and this was C3H7. Okay, I think that's right. Let me check. 6, 7, that's right. Do we all understand that I've rewritten it in the kind of shape it is? I've rewritten it in a tetrahedral shape. Does that make sense? Are we good? Yeah, well done. It's exactly the same molecule. I've just drawn it a little bit different. Now this bromine here is big. Okay, bromines are big. Okay, and not only big, but it's also delta negative, isn't it? And this carbon is delta positive. Yeah, it's tetrahedral for sure, Tamani. Yeah? Now, you know what? One thing I should do with you guys is, and I will do it, remind me, well, I'll try and remind myself on Monday. We'll look at some software, okay? Because you've got to start realizing the shapes of these things. All right. It's free software. Hold on, what's it called? And unfortunately, the machine I'm on at the moment, Cam Sketch. The machine I'm on the moment is brand new, like 2 weeks old or whatever. Okay. Now I'm going to give you here, Control C. I'm going to go to the chat box. Okay, there. Now I've sent you a message there, and that's a free software, and it enables you to draw these things. It's really good. All right, it's a really good piece of software. Unfortunately, as I say, I haven't loaded it on this machine yet. Okay, but that's what I'm going to do after this lesson. I'm going to put that on this machine, so I've got it for Monday, and I'll show you about it. But it's a beautiful piece of software, and it's free. Okay, you've just got to say you're using it for academic reasons. You're not obviously going to use it for financial gain. But there you go. That's a really good software, and I'll show you how to use it on Monday. All right. But please download it if you can. Okay. This is why I must admit that's what students should all. I think tablets are lovely, but I think honestly laptops are nicer for these sort of things. All right, it's a bit easier. I don't even use a laptop anymore. Well, I do at school, obviously, but I use a desktop. I just like the speed of desktops. Yeah, but that's the shape of it. Okay. Anyway, so that's bromo, whatever it is, bromo, whatever, bromo. Oh, is it C3? Oh, I think I've done the wrong one here. Sorry. I've got one too many carbons there, haven't I? It's not C3H7, is it? It's, where are we? It's actually C2H5. All right, but it doesn't matter. It's the same thing. And as you can see, it is a primary. This is a primary halogen alkane. Okay, now my OH, where's my OH? My OH is here. Okay, like exactly what we did before, and there's the lone pair. Okay, so my lone pair is there. Let me get rid of that ugly oxygen. There you go. Now, look at this. Now, the way we did it before, I just did it kind of two-dimensionally, but now I'm trying to show you three-dimensionally. All right, and now these electrons, they try and attack from the front, but because these are negative and this is negative, it is repelled from the front. So it doesn't attack from the front. It attacks, believe it or not, from the back over here. This is OH minus, and there's 2 electrons there. So it can't attack from the front because it is repelled by the bromine. So that doesn't happen. Are we okay for that? So what does it do? It attacks from this side. Are we good? I'm going to get rid of this now. It attacks from that. It's just life, I'm afraid. Yeah, Janet's a bit confused. Well, Janet, if you think of this thing, it is a tetrahedral. Okay, there it is. This is how we show organic things. That kind of gives it a shape. Okay, what does the wedge mean? Now let me explain this thing. This straight line means it is in the plane, same plane as the monitor or the blackboard or whatever I'm writing on, whiteboard, blackboard. This full line means it is on the same plane as the monitor. All right, are we okay with that? Those 2 straight lines or the 2 full lines mean they're on the same plane as the thing you're looking at it on. This one, the wedge, these are known as wedges. This is a wedge. And this implies it's coming out of the monitor. It's coming towards you. And this dotted line that I haven't drawn very nicely there, that implies going into the monitor. Okay, so if you kind of have a good imagination, you can look at this shape and kind of see a tetrahedral. Does that make sense, Janet, now? You could kind of see a tetrahedral. And this is how all carbon atoms are. All, and I mean all, this is how all carbon atoms are when they are sp3 hybridized. Now, I know some of you understand that term and some of you are a bit shaky on it, but trust me, if it's sp3 hybridized, it must be in a tetrahedral shape. And just as importantly, if it's in a tetrahedral shape, it must be sp3 hybridized, okay? So everything I'm looking at on the board here is sp3 hybridized. They're all in this tetrahedral shape, okay? Don't forget, when we draw methane, we draw this, don't we? We draw a very boring thing here. But actually, methane looks like this. It is a tetrahedral. Are we okay with that? Are we good? Excellent, well done. Now, crazy but true, I'm going to rub this off in a minute. So this guy is in a tetrahedral, but some of these two, it's tetrahedrals connected to tetrahedrals. We don't bother with them often because it's not the part of the molecule we're looking at, but they're all tetrahedral. Yeah, it's tetrahedral all the way down. Right, now I'm going to get rid of this. And don't forget, I'm recording this. So if you're confused about that, you can look that up. Okay, this is taking forever. All right, so there you go. Right, now I think the video is going to stop in a minute, but don't worry, it gives me a like 30 seconds notice. And when it does, I'll start recording again. So what we've got is this, and at the same time, these electrons go onto the bromine. Okay, and now we get this C, H, C2, H5, where are we? H, and we've got the OH coming into this shape. Dot, 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 dot. And we've got the BR, I think my internet's dying because this is taking a long time to draw, coming out. Now, this is a confusing shape, but what it is, these guys